Hello, dear students. Hope you're doing great. Welcome back to Bridge Academy Grade 11 Geography Lessons, yet another exciting episode. Unit 1, Formation of the Earth's Continents. Lesson 4, Relative and Absolute Age of Rocks. At the end of this unit, you will be able to ascribe the difference between relative and absolute ages of the Earth's rocks. Introduction. The geologic time scale helps us understand Earth's 4.6 billion year history by organizing it into time units. To create this time scale, scientists must know how old rocks are. The previous lesson explains two ways to find the age of rocks: relative age and absolute age. Relative age shows which rocks are older or younger without exact years. Absolute age gives a precise age in years. These methods help scientists place events, landforms, and life in the time scale. This section will explore how relative and absolute ages work, how they are used, and why they matter for studying Earth's past. Relative age is about finding the order of rock layers. It does not tell us exact years. Scientists use a method called stratigraphy to study rock layers, also called strata. The law of superposition says older layers are at the bottom and younger layers are at the top. For example, in a place like the Grand Canyon, the deepest rock layers are the oldest. By looking at these layers, scientists can tell which rocks formed first. This helps them put events in the right order for the geologic time scale. Fossils are important for relative age. Each time period has different fossils. For example, rocks with trilobite fossils are from the Paleozoic era, while rocks with dinosaur fossils are younger, from the Mesozoic era. If scientists find the same fossils in rocks from different places, those rocks are the same age. This process is called correlation. In the 1800s, a scientist named William Smith used fossils to match rock layers across England. Correlation helps scientists connect rocks around the world, building the timescale's timeline. Relative age has some limits. It shows which rocks are older or younger, but it cannot give an exact age in years. For example, we know trilobite rocks are older than dinosaur rocks, but not by how many years. Radioactive isotopes are unstable atoms that change over time. They decay into other elements at a steady rate. For example, uranium-238 decays into lead. The time it takes for half of an isotope to decay is called its half-life. Each isotope has its own half-life. Uranium-238 has a half-life of 4.5 billion years, so it's good for dating very old rocks. Scientists measure how much isotope is left in a rock and how much has decayed. Using the half-life, they calculate the rock's age. This gives a precise number. To get exact ages, scientists use absolute age. Absolute age tells us a rock's age in years, like 200 million years old. The main way to find absolute age is through radiometric dating. This method uses special atoms in rocks called radioactive isotopes. Radiometric dating made the geologic time scale more accurate. For example, scientists used it to date rocks from the asteroid impact that killed the dinosaurs. Those rocks are 66 million years old, marking the end of the Cretaceous period. Radiometric dating works best with igneous rocks, like those from volcanoes. Sedimentary rocks, which often have fossils, are harder to date directly. Scientists date nearby igneous rocks to estimate the age of sedimentary layers. This helps place fossils in the time scale. Relative and absolute ages work together to build the time scale. Relative age gives the order of rock layers and fossils. Absolute age adds exact dates. For example, in the Grand Canyon, relative age shows that deeper layers are older. Radiometric dating shows those layers are 1.8 billion years old. Together, these methods help scientists know when mountains formed, when seas covered land, or when animals lived. This creates a clear picture of Earth's history. Using these methods can be tricky. For relative age, rock layers must be clear and undisturbed. Earthquakes or erosion can mix layers, making it hard to read them. For absolute age, rocks must have radioactive isotopes. Not all rocks do. Some rocks, like limestone, have few isotopes to measure. Scientists solve these problems by combining both methods. They use fossils for relative age and radiometric dating for absolute age. This makes the time scale reliable. The ages of rocks help us learn about Earth's past. They show when landforms, like the Himalayas, formed. They also show when life changed. For example, the Permian extinction, dated to 252 million years ago, killed most sea creatures. Fossils and radiometric dating place this event in the time scale. Knowing rock ages also helps find resources. Oil often forms in rocks from specific periods, like the Jurassic. This connects Earth's history to our lives today. Relative and absolute ages also show how Earth's processes and life are linked. For example, volcanic rocks dated to 66 million years ago match the time dinosaurs went extinct. This suggests volcanoes or an asteroid caused the extinction. By dating rocks, scientists see how events shaped life. The time scale uses these ages to tell Earth's story from ancient oceans to modern mountains. Summary: relative and absolute ages of rocks are key to the geologic time scale. Relative age uses rock layers and fossils to show which rocks are older or younger. The law of superposition and correlation help with this. Absolute age uses radiometric dating to give exact years. Radioactive isotopes and their half-lives make this possible. Both methods work together to place events in the time scale. They show when landforms and life appeared. Challenges, like mixed layers or missing isotopes, are solved by combining methods. Rock ages help us understand Earth's history, find resources, and connect processes to life over 4.6 billion years. Review questions and answers. 1. What is relative age in the geologic time scale? Answer: relative age shows which rocks are older or younger using rock layers and fossils without giving exact years. The relative age is a way to determine the order of rock formation, whether one rock is older or younger than another without specifying exact ages in years. It relies on observing rock layers, strata, and the fossils they contain. Relative age focuses on sequence, not precise dating. 2. How does the law of superposition help find relative age? Answer: the law of superposition says older rock layers are at the bottom and younger layers are at the top. 3. What is absolute age and how is it measured? Answer: absolute age gives a rock's age in years measured by radiometric dating using radioactive isotopes and their half-lives. 4. Why is radiometric dating important for the time scale? Answer: radiometric dating gives exact ages, like 66 million years for the dinosaur extinction, making the time scale more accurate. 5. How do relative and absolute ages work together? Answer: relative age orders rock layers and fossils, while absolute age adds exact dates, helping place events in the time scale. Thank you. Do not forget to like, share, and subscribe. See you next time.